Okay, we're going to talk about two main types of friction. First of which is kinetic friction. What does the word kinetic usually mean? Movement. Okay, just like the word kinematics, those are our kinematics equations. They deal with velocity, acceleration, movement. So when we say kinetic friction, we're talking about the friction that's opposing the object while it's in motion. And when we talk about friction, friction isn't always necessarily going west, right, on our free body diagram. It's going opposite of the motion or opposite of my applied force. That's really important. So if I would look at a free body diagram in which my applied force is to the left, what direction would my friction be going? To the right. My frictional force would look like this. And we abbreviate it F sub little f for friction. Okay, so it doesn't always necessarily go to the left, but it always opposes the motion. When we talk about friction, there's a couple different things that influence friction. The first thing that influences friction is basically the two types of surfaces. Okay, if I've got an ice cube sliding on ice, do we think we have a lot of friction there?
No.
Not so much, right? But if I have sandpaper on carpet, friction, yes, no?
Yes. Yeah.
Yes. Okay, so it depends on the two surfaces. It's also found to be proportional to the normal force. Okay? The kinetic friction and the other type of friction we're going to talk about, friction is proportional to the normal force. Okay? And what does normal force usually equal if something is at rest? Or it's just, kind of sliding? What's the normal force equal to if something's sliding just horizontally? Good. It's equal to the force of gravity, right? The normal force and the gravitational force would be equal. So we can also kind of think about kinetic friction or friction itself being proportional to the weight of an object, okay, or the normal force specifically. We're going to plug the normal force into this friction equation. So I want to demonstrate basically this last little bullet here to you. Okay, I want you to just rest your hand really lightly on your table. Okay, really lightly. Then just try to move your hand. Just slide your hand. Is it really difficult? No. Not so much. Now I want you to push down and increase the normal force. Now try to slide your hand. Okay? It makes a difference, right? It's a lot harder to slide your hand as you increase that normal force. As you push down, you are increasing that normal force. You can kind of think of it as those two objects kind of really meshing together and increasing the friction, if you want to think about it like that, right? But as we increase the normal force, we see an increase in our frictional force, okay? The equation that goes with frictional force is this right here, and it will probably need to go on your equation sheet, okay? I'll write it up here a little bit bigger, and I'll explain what that means, okay? It's the force of friction equals the coefficient of kinetic friction times the normal force. Okay, this is a Greek letter called mu. Mu. It's a U with a little tail on the front. And it is a coefficient of friction. The coefficient of friction is solely dependent upon those two surfaces. So there is a coefficient of friction on a wood surface to a wood surface. There's a coefficient of friction for ice versus ice. There's a coefficient of friction for carpet versus wood. There's all kinds of different coefficients of friction that have been proven for those two surfaces. Okay, so you'll be given a coefficient of friction based on the two materials, or maybe you would have to solve for the coefficient, something like that. Something that you should know is that the coefficient has no units. Okay, the coefficient has no units. Because if I have frictional force is equal to the coefficient times the normal force, the units for this are newtons. Coefficient times newtons. So if I solve for the coefficient, I would divide by the normal force, which is newtons. Divide by the normal force, which is newtons, which cancels out, which means my coefficient can have no units. Does that make sense? So no units for the coefficient. So the second type we're going to talk about is called static friction. What's it mean if something remains static?
Still.
Still, right? Not electricity. We're not going there. Static means it's still, it's not moving. Okay, so static friction means it's the frictional force that's applied on an object when it's at rest. Frictional force applied on an object at rest. So in order to put an object into motion, you have to get it started, right? You have to overcome that static friction. So when you apply a force to get things started, like pushing something or pulling something, you have to apply enough force to overcome friction. Something that we can think about here is that when you are doing this, when you're pushing or pulling on something to overcome static friction, the very, very instant that you apply enough force to overcome that, those two forces would be equal to each other. So the very instant in which that object starts into motion, the frictional force and the applied force are equal. After that, your applied force would be greater. Okay, so there's an instant in time where those two are equal. But yeah, here is our equation for this. Okay, and you don't need to write maximum. Okay, I really would just want you to keep it at the frictional force is equal to coefficient of static times the normal force. Why do you think it might say the maximum frictional force there? Why do you think your book calls it this maximum? I'm not going to have you label it like that, but why would it have you call this the maximum frictional force?
Because it's all of it added up. The force of, like, it's staying and the force of viewpoint.
It's the most you can have while at rest.
Yeah. Your friction is the greatest when it's at rest. So that's why this is your maximum frictional force. This is the greatest friction you could ever have, right? Once you start moving, you have less friction. But this is the greatest that you would have. Realistically, when we write our friction equations, I don't even need you to put the subscript there for kinetic or static. You just need to know which one you're dealing with. Okay, I'm not going to be really concerned with you keeping that coefficient, but you do need to understand there is a difference between the two. Okay. Okay, so we're not going to read this 96. Okay, sorry. Which value should be higher between the two objects, the coefficient of static friction or the coefficient of kinetic friction? Static, good. So whenever we look at coefficients, our coefficient of static friction should be much higher than our coefficient of kinetic friction. So if our coefficient... Okay, so in order to find basically the horizontal acceleration, which is what we're looking for, we're going to have to take a lot of steps to get there. I wrote out every single step. When we do these problems, I'm not going to write out the steps, but you'll start to understand the process you need to go through to get there. You got to think about what things you need in order to solve for that acceleration. But our overall goal here is to find A. Okay? So first thing that we need to do is draw a free body diagram. Always start with a free body diagram. As we move forward into these two-dimensional forces and we start to get a little more complex, having that free body diagram is crucial. If you forget forces, it's going to throw your whole problem off. So please be really, really disciplined with that. Okay, we've got a sled. What forces do we have here?
We have friction.
Okay, normal force first. We'll say normal first. Gravitational, good. Okay, should our applied force...
Right.
Okay, to the right. Why do we think maybe to the right? It's a positive force, yeah. And just most of the time we think that things are going to go in the positive direction. Okay, so this is force applied. And then what else do we have?
Friction.
Friction. All right, good. Does this mean our frictional force is 0.01?
What?
No, that's just the coefficient equals 0.01. All right, so let's start looking at how we're going to get to this. What I'm going to do first is I'm going to set up my net force equation so we can see where we're going here. We want horizontal acceleration. So does that mean I want to look at horizontal forces or vertical? Horizontal. So I want to say F applied minus force of friction. Okay, and I'm even saying here in these steps to calculate the frictional force separately, then plug it in. I just want to do everything in one equation. You don't even have to break it up, okay? So let's look at our substitutions we can make. What can we always substitute for F net? MA, so equals force applied, which we know is 75. And what can we substitute now for the force of friction? No. Good. We know our frictional force is coefficient times the normal force. So this is going to be another one that we can substitute. 0.010 times the normal force. And we don't know the normal force yet. Do we? Have we calculated that yet? No. Together? Okay, we haven't calculated it together. So now we've got a couple different things missing. I know the mass, so I can go ahead and plug that in here. I didn't mean to put the M. I know that my mass is 50 kilograms. So now I've got two variables, acceleration and the normal force. So that's not going to work. Nope. Which of those can I solve for?
Force of gravity, yeah, what she said.
Okay, what's solving the force of gravity going to do for us?
It's going to give us the normal force.
Good. So out of these two variables, acceleration and normal force, we can find the normal force to plug it in and solve for acceleration. So if we know that the normal force is equal to the gravitational force, we can say Fn equals Fg, right? Which is equal to mass times 9.8. Which gives me a value of about 490. Right? Is that correct?
Sure. That's what the normal force is.
So once we find our normal force, we're going to plug this in right down here. We're going to take 490 times 0.01. So that leaves us with 50. A equals 75 minus 4.9. Okay, and what do we get for our acceleration here? Are you ready to try this one on your own then?
Yeah.
Yeah?
For sure. Yeah, let's do it.
Okay, this one is basically exactly the same as the last one.
If we get this.
All right, so let's take a look here. Raise your hand if you agree. Raise your hand if you agree. 1.19 or 1.2?
Yes.
All right, very good.
Yeah, y'all just agree with it.
All right, so this tells us a box is sitting on a wooden floor. They pull upward on the box with a force of 100 newtons at 40 degrees. The box begins to slide, despite that the coefficient is 0.3. So our overall goal here, again, is to find the acceleration. So I'm going to give you a couple minutes to get it written down, and then we'll start working. Can we visualize what's happening here? We're dragging something on the floor. You're just lifting it like this, okay? You're just dragging something. It's sliding on the floor, so that means you just have to be walking, pulling it, it's sliding. It's not coming off the floor in any way. All right, let's start with our free body diagram here. We've got gravity, the normal force, because it's not leaving the floor. Our applied force this time is not just horizontal, it's at an angle. Okay, and when we say 40 degrees, where does that fit on our diagram? Above or below?
Below.
Yeah, right, it goes to the horizontal. So 40 degrees right there. This is 100 newtons. Okay, and we've also got friction, which would friction go like this? No, it's going to go horizontal, right? Because our box is still on a horizontal surface. So here's our frictional force. Okay, so the first thing we do when we see a force at an angle, what's the first thing we do? Yeah, we break it down. We break it into components. So how do we go about breaking this into components?
100 sine 40.
Okay, if this is F applied, what do we call this side? Yeah. F applied Y. And we would call this F applied X. Okay, that's just the X and the Y components of our applied force. So let's solve for F applied Y here. Would we use sine or cosine?
Which angle are we trying to find?
We're not trying to find an angle at all. We're trying to find these sides.
Okay.
We're doing Y right now. We would use sine.
So, you're taking from 40 degrees and the sine is opposite.
Opposite over hypotenuse.
Because
We're trying to find this opposite side. For X, we're trying to find the adjacent side, so we're going to use cosine. Okay, I cannot keep talking over you. Okay, it needs to be quiet. Okay, so can someone raise their hand and give me a value for Y? 64.28. Okay. And what is the value for X? 76 point what? 6. All right. So now we want to find the acceleration, right? Do you think we're looking for vertical acceleration or horizontal acceleration? Horizontal. Okay, so let's set up our net force in the X direction. I'll make it a little different color here. This is just to see where we're going here. We're looking for the F net in the X direction because our overall goal is to find the horizontal acceleration. So how many horizontal forces do we have? 2. 1, 2. Okay, the X component is now considered a horizontal force because once we break down the 100, we don't use it again anywhere. Okay? Once we break down that component, we don't use it again anywhere. So we're going to take F applied X minus the frictional force. Okay, is everyone on the same page right here?
Sure.
Okay. Let's do our substitutions now from one to the next. So mass times acceleration equals F applied X. I'll put the numbers in a second. Okay, I'm gonna put the numbers in the next one. What can we substitute for the frictional force?
It's the U thing.
The U thing, yeah. Okay, the coefficient times the normal force. You don't have to write down every single one of these steps. I am just showing you exactly what we're doing, where we're getting these numbers from. So now let's put in numbers. The mass is 30. Acceleration is what we are solving for. F applied X is 76.6. The coefficient is 0.3. And we don't know the normal force yet.
So
Now we need to find the normal force. Is the normal force just going to be equal? No, it's not. It's not going to be just equal. Because how many vertical forces do we have? 3. 1, 2, 3. So now we have to solve for the normal force. Okay, this is kind of like what we did last class where we had this applied at an angle. Stay with me here. Okay. Now let's set up our net force in the Y direction to solve for the normal force. I know these takes a lot of work. You have to stay with it. Remember what your overall goal is here in mind. Right now we're solving for the normal force. In the Y direction, because we have to basically be able to set up that net force in the Y direction to solve for the normal force. Since it's not just equal to the gravitational, because we've got 3 forces. Okay, so we need to set up normal force plus F applied Y minus FG. Okay, why are these two both plus? They're both going upward. They're both going in the upward direction. We're going to subtract out gravity. So what is my net force in the vertical direction here? Is my object moving in the vertical direction?
No. Oh, yes.
No, it's just sliding. Right here, this right here tells us begins to slide. That's telling us our motion is purely horizontal. So vertically, does it have any acceleration?
No.
No, which means this is 0. So normal force plus F applied Y, which we know is 64.3. And what do we know Fg is always equal to? Mass times gravity, so 30 times 9.8. 294. So 64.3 minus 294 gives me what value? 230 something? 220? 229.7. So our final step here to solve for the normal force would be adding that to the other side, which would give us a normal force value of 229.7. Now we can go through, combine these, divide by 30, and solve for our acceleration. Okay, so we got our acceleration to be 2.256. Let's try this one on your own. Try this one on your own. Okay. Okay, so as you look at my final kind of net force equation in the x direction, did these numbers match what yours were?
No.
For the frictional force, 189, somewhere around there?
That was like I got one.
How many of you came up with the negative acceleration here? What does a negative acceleration tell us in this case? The negative acceleration is telling us that friction is pulling it backwards. Does that happen?
No.
No. Look at our frictional force here, 189. Look at our applied force, 168. Is our applied force enough to get it started? No. So the answer to this is it won't move.
Oh my gosh.
Okay, it doesn't even have an acceleration. It's not going to move. If the frictional force is less than the applied force, it would move. If it's greater than the applied force, it's not going to move. So see what you can do to try and solve for this one. I'm going to look at these and then we'll go together. See if you can get started on this one.
Oh, I know this. Okay, solve the coefficient. Yeah.
No, I'm not going to get hard. I'm going to solve this one.
Zero. What about 700 billion? 687 billion. Why? No, it's way too risky. No bounce back.
Okay. It doesn't tell us an angle here on our applied force, which means we assume it's purely horizontal. So it's no angle this time. We don't have to break anything down. Do you think we should be looking at the horizontal forces here or the vertical? Horizontal first. We're going to eventually need both because we need the normal force, but we're going to look at horizontal first. So we would take F applied minus frictional force. We do our substitutions. We were given our acceleration this time. Okay, how do we go about solving for our normal force this time?
Just do the same. Force gravity.
Yeah, it's equal to the gravitational force this time, right? Just those two forces. So we would take 90 times 9.8.
Equals 882.
Okay. So I'm going to get rid of this in here. So algebraically, we'll do this first. 90 times 1.2. Okay. 108 equals 320 minus the coefficient times 882. We want to subtract that over. So there's a couple things we should know about the coefficient of friction. First of all, it should never be negative. The coefficient of friction should never come out negative. The coefficient of friction also is usually between 0 and 1. Usually. Okay, we'll see some instances where maybe we get up in the 1.2 to 1.5 range, but more often than not, we have a coefficient of under 1. If you get a coefficient of like 16, you did something wrong. Okay?
How did